biologists, welcome back. We are now past the scientific method and we're going to move on to chemistry. Yay! Your favorite subject. I know that you like chemistry, that's why you took a biology class. I know, kind of sucks, but the reality is to understand the basics of biology and how biological molecules are put together, we do need to cover a little bit of chemistry, but not like a huge amount. We're actually going to go through what I like to call chemistry light. Chemistry just for biologists. I'm going to go ahead and turn off my camera now so that you can concentrate on the PowerPoint presentation. And so here we go. Chemistry. But wait, this is a biology class. Why the heck am I having to learn chemistry? Well, it's actually very simple. Organisms, all those great things that we love, plants, dogs, elephants, they're all made up of tissues. All those tissues are made up of cells. Those cells are made up of organelles, little things that we're going to learn about later. These things are made up of molecules, and whether you like it or not, molecules are made up of atoms. So atoms really are the building block of all life. And I know it's not like this whole class is going to be chemistry, but at least this lecture and next lecture will be chemistry. And then from that point on, you will be a chemistry expert, and we'll be able to continue on and talk about biology and all understand each other. So what is chemistry? Well, chemistry really is just the study of composition. It's the study of how stuff is put together, matter, the structure of matter, and the transformation of matter from one substance to another. And that's pretty much it. You know, biology falls within this realm, but it's not just biology. Chemistry pertains to geology, you know, rocks, the ocean, the atmosphere, space, you name it. Everything has to kind of revolve around chemistry. But the chemistry that is specific to biologists is known as biochemistry. And one of the most important things for us to study in biochemistry is chemical reactions within our bodies. And I've listed 3 chemical reactions here that are essential to life on the planet. The one that is important to us, the 2 that are important to us, respiration and digestion, are really essential. We're going to actually go into great length on these 2, but photosynthesis, very, very important. This doesn't happen in your body, but believe it or not, you do rely on photosynthesis a lot. Everything you eat relies on photosynthesis. I mean, this little guy right here eating whatever that is. I'm not quite sure what he's eating, but anyways, that relies on photosynthesis as well. So let's take a look at what chemistry truly is, just, I mean, really at a basic level. Here's a guy eating a hot dog at a baseball game, and he's going to chomp away at that food and break it all down in his stomach, and as you break it down, it looks like that. Alright, so that's very simplified, but let's say that you're breaking that stuff down, and now you're going to use that material. You've broken it down, you're using that broken down material to then build yourself up. You're going to combine that atom, all those little atoms that are now floating around in your stomach and have now made it into your bloodstream, and we're going to combine them using a chemical bond process that we'll discuss later in order to make muscle tissue, like this woman that has unusually large muscles. But anyway, this is how all of your body functions work. They work basically just like this. And obviously we're going to get into more detail on this. It can't be quite this simple, but this is at least it in a nutshell. That's a molecule, by the way. A molecule is just a construct of many atoms being put together using chemical bonds. Now, this is called the periodic table. All of those fundamental forms of matter that are elements can be shown on this periodic table. Each one of these boxes is a unique element, and each one of these cannot be broken apart by normal means. That is, if you were to pulverize things and actually be able to break them apart, they are no longer elements at that point. These are the smallest units that retain elemental properties, and there are 92 of them that occur naturally on Earth. You'll notice there are more than 92 boxes here. That's because it's possible to make them unnaturally, some of them unnaturally, in a laboratory. We're only going to focus on what occurs in nature, though. So 92 occur naturally on Earth, and of those 92, your body only requires 25 of them. Now, This is all of those things in your body in a nutshell. All of the elements, all of those atoms in a nutshell. And their proportions, their relative proportions. This column over here gives you their percentage by body weight that they make up in your body. And you'll notice that some of them, these top 6 for example, are more abundant than others. And these are the ones that make up at least 1% of your body weight. You'll also notice that oxygen and carbon have a disproportionately high abundance in your body. Does that mean that oxygen and carbon are more important than the others? No. I want you to think about a car. How much gasoline do you put in your car, your gas tank? Let's say that your car can hold 15 gallons of gas. And let's say that your car also holds 5 gallons of, not 5 gallons, half a gallon of oil, and maybe a quarter of a gallon of brake fluid. Well, you know, by the faulty logic, you might think, oh, hey, gasoline's more important because I need more of it. Oh, yeah? Try running your car without brake fluid or without oil. It still wouldn't run, would it? They're all equally important, even if one is occupies more of an organism than another. Just like even though gasoline, there's more gasoline in your car, it doesn't mean that it's more important than the oil or than the brake fluid. And notice also that there's a lot of elements, like these ones down here, that are in small amounts. And even these ones down here are in trace amounts. They are in very, very small amounts. And yet, they are essential. Very, very important, these trace elements. You need trace elements. I'm going to just give you some examples of if you didn't have them, you'd have a bad time. Iron deficiency. You cannot function without the proper amount of iron, and it becomes even more important as you get older, particularly for women who develop iron deficiencies. Men can develop iron deficiencies as well, but it's disproportionate in that it affects women more often than men. Another one that is equally important for men and women is iodine deficiencies. Iodine is one of those trace elements that you need in very, very small amounts, but if you don't have any of it, you develop major thyroid problems like this poor woman here. Now, this problem was largely solved in the United States, the iodine deficiency issue, because about 80 or 90 years ago, we kind of made an ordinance here in the United States that all salt was going to be sold with small amounts of iodine added to it. And you've probably seen it in the store, iodized salt. So even though you probably shouldn't be eating very much salt in your diet, you know, you should be eating good amounts, you know, small amounts. You know that at least you're not going to have iodine problems if you live here in the United States, because all of the things that are seasoned with salt have a trace amount of iodine added to them. So congratulations to us. We actually have been doing this for a long time, adding nutrients to food or adding trace elements to food. We know them as fortifying the food, whatever that means. This is a nutritional facts on the side of a total whole grain breakfast cereal box, and you'll notice that it's fortified with a whole bunch of things here. And you might think, oh, maybe they fortified it to make it more healthy. No, actually that's not true. You see, processed food, highly processed food, like this food grain right here, this breakfast cereal, in the processing or the formation of this processed food, a lot of the normal or natural nutrients are totally cooked out of it. So they actually have to re-fortify it to bring it back to the nutritional value it had before you processed it. So the lesson here, just eat raw foods. Steer clear of processed foods, and you won't have to have them fortified. We'll talk more on that later. Alright, so we were talking about atoms. And so let's come back to atoms. What are atoms? Well, really, atoms are the smallest possible particles that retain its elemental property. And they are made up of subatomic particles. Subatomic particles are what atoms are made of. And actually, there's a whole bunch of them. We're really, in this class, we're only going to focus on 3 of those subatomic particles. Protons, which have a positive charge, electrons, which have a negative charge, and neutrons, which have no charge at all. And then, of course, don't forget, there are other elements as well. We're not going to focus on them here. But when you take these atoms, which are made up of protons, electrons, and neutrons, and you combine them, they end up forming compounds. So a compound is really just a substance of two or more elements. And in fact, lots of compounds have only two elements, but there's a lot of compounds that you encounter that have a whole lot more than two elements. So this is a really good example of a compound, water. Water is a compound. It's made up of two elements, hydrogen and oxygen, and it's made up in these parts, 2 parts hydrogen to 1 part oxygen. You've probably heard of it as H2O. Hydrogen and oxygen are gases. When you combine them in this combination, it makes a liquid. So it has a property. Water has a property that is very different from the constituent elements that it's made of. And so, case in point, here's a really good example, table salt. Table salt is actually made up of 2 elements as well, sodium and chloride. And yet, interesting, as essential as salt is, you do need small amounts of salt in your body. And yet, sodium, which is one of the salt components, is a metal when it is just pure sodium. And chloride is a gas. In fact, it's a poisonous gas, which is kind of strange because when you combine sodium and chloride, you make table salt, which is an edible compound. So that's kind of interesting. It goes to show that a compound is not necessarily or does not necessarily have the properties of the constituent elements that make it up. Okay, let's move on to how atoms are constructed with those protons, electrons, and neutrons. One of the guys who kind of helped us understand how atoms really behave at the atomic level is this guy Niels Bohr. And we refer to his models as the Bohr model of the atom. And he won actually a Nobel Prize in Physics in 1922 for teaching us this. Let me give you a couple of really good examples. On the left is the atom hydrogen. On the right is the atom helium. And hydrogen has 1 proton and 1 electron in it. Hydrogen does not have any neutrons. Helium, on the other hand, has 2 protons, 2 neutrons, and 2 electrons going around it. Well, that's kind of convenient. Now, it's important to know, though, that while this is a nice little drawing, you could actually draw this out on your notepad right now, where you have your nucleus. Your nucleus is the center of the atom, where your neutrons and your protons reside, and then you have your orbit out here where the electrons are. The electrons are circling around in an orbit, and drawing these as little dots with lines as circles for the orbits kind of gives this impression of like the moon circling around the Earth or something like that. But in fact, it really isn't like that. Bohr's model is really just an approximation. Yes, we like to think of electrons as little particles that are circling in an orbit, but the reality is those electrons are traveling so fast that they're really occupying the entire orbit at the same time. So on the left here is a cloud of negative charge. That's more accurate. That's probably what an atom, if it was possible to shrink yourself down and look at an atom, that's probably more like what you would see. Okay, so how do we organize atoms? How do we actually make sense of atoms if we're counting up the number of protons, neutrons, and electrons that make up the atom? Well, we use the periodic table once again. And this is one element that's been pulled out of the periodic table, helium. You are probably familiar with helium. It's what they put in balloons to make them float, and then you breathe it, and you have a really high, funny voice. So in this case, there are a series of numbers and a series of symbols and other things here. We're going to go through each one of these and explain them. The one I want to talk about first is this number at the top, that 2. That's called the atomic number. The atomic number is the same as the number of protons. So if you recall a couple of slides ago, I showed you a helium atom, a Bohr model of a helium atom, and there were 2 protons in the nucleus. So that's where we get that number 2. That's the number of protons. Just as an example here, all atoms of an element have the same number, same atomic number. So for example, if you were to take a helium atom here in Southern California and compare it to a helium atom in Antarctica or something like that, the number of the atomic number would be identical. The number of protons would be the same in each of those helium elements. So here's some other really good examples of atomic numbers. Hydrogen has an atomic number of 1, meaning it only has 1 proton in there. You saw that before. Helium has an atomic number of 2 because of the 2 protons in it. Carbon has an atomic number of 6 because it has 6 protons in its nucleus. Okay, let's go on to that bottom number now, the atomic mass. The atomic mass is a combination of protons and neutrons. And this is a little bit more of a nebulous idea. If you go back to that slide where we were looking at the helium, you remember that there were 2 protons and 2 neutrons in the nucleus. So if you added up 2 and 2, you should get 4. And in fact, for all intents and purposes, 4 is the atomic mass for helium. But you might be confused and you might say, well, wait a minute, why is it 4.003? Why is it not exactly 4? Well, let me explain it a little bit to you here. I'm not going to go into great depth on it, but you know, for some purposes it will be important for us in the future. So the answer is that on rare occasion, you can get a helium atom that might have more than 2 neutrons. You can't change the number of protons. As we mentioned before, the atomic number is the number of protons that defines the element. However, on occasion, you might have 1 extra neutron. Because remember, a neutron is neutral, so it doesn't change the charge of the element. And so if you had 1 extra, it might be stable for a little while at least. So if you were to take a whole handful of helium atoms and you were to weigh them, the atomic mass might be a little bit more than 4 because on occasion you might have a few of those helium atoms in there that have more than 2 neutrons. They might have 3, for example. And those kind of odd atoms, we call those isotopes. So the isotopes, the occasional isotopes, are what make the number a little bit more than what you might predict, more than just that 2 plus 2. Let me talk a little bit more about isotopes. This is them defined. I just defined them for you in the last slide, but here they are again. Protons, remember, they don't change for an element. They must stay the same. Every element has the same protons no matter where you are in the universe. But the neutrons can change. And when the neutrons change, we call those isotopes. And I've defined that here as an isotope are 2 atoms of an element that have a different number of neutrons. So why is this important? Well, when we have a lot of isotopes, especially those that are not stable, we call those radioactive isotopes. That is, just by random chance, atoms kind of bombarding around in space, every now and then you might acquire a couple of extra neutrons. And a really classic example of this is carbon. On the left here is carbon-12. Carbon-12 is, you can think of it as normal carbon. It's listed here as stable carbon. The vast majority of carbon in the universe is this kind right here, carbon-12. It has 6 electrons, it has 6 protons, it has 6 neutrons. But on occasion, carbon can acquire up to 2 extra neutrons, not protons. Protons are the same, has the same, charge and all of that, but the number of neutrons is extra, 2. So we can think of it as unstable carbon. You can think of it as radioactive carbon, carbon-14, or you could call, actually carbon-14 is normally what we refer to it as, or irregular carbon, if you wish. Now, carbon-14 being unstable, it doesn't stay like that for very long. Eventually, it's going to degrade and break down into carbon-12. But however, you can tell the difference between carbon-14 and carbon-12, the fact that it's radioactive. All you need is a special machine, and if you take carbon-14 on purpose, you can actually use it for medical applications, to actually track things in your body by looking at where the carbon-14 isotopes go. Here's a couple of really good examples of uses of isotopes. Particularly in carbon, we use them as metabolic tracers. So, for example, let's say you're going to give something to plants. You're going to look at where photosynthesis is taking place in a leaf, like this leaf right here. You can actually charge the carbon in the air around this leaf. They use carbon dioxide that comes out of the air. Well, you can actually charge the carbon dioxide in the air using C14. And when the plant incorporates this carbon from the carbon dioxide into their leaves, you can actually watch it incorporate the C14 directly into its leaves. And because you have a machine to detect the C14, you will know where all of that C14 goes. Oh, that's kind of cool. Another kind of use of the carbon isotope is in half-lives. So we can actually use this concept to age objects that are made of carbon. The classic use of this is in fossils, determining how old fossils are. C14, when it is spontaneously made, it actually breaks down at a known rate, at a known speed, if you will. That is to say, C14 breaks down, and it's no longer C14, in about 5,730 years. Give or take 40 years, to what's called a half-life. That is to say, if I had a box of C14 and it was sitting on my desk, 5,730 years later, on average, half of that box would no longer be C14. It would be some other element, either C12 or something else. And then another 5,730 years after that, half of the remaining C14 would have broken down. So now there's only a quarter left. Another 5,730 years after that, the remainder of that would then break down. Half of the remainder of that. So that's what half-life is all about. So if you were to take a bone fragment, let's say, and you were to measure the amount of C14 in it, and it had very, 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 very little C14, you could surmise, knowing this breakdown curve right here, that it was a very old fossil. And in fact, there are mathematical formulas that you can apply to this to estimate the age to a very accurate age, actually. And that is how we know dinosaur fossils are somewhere between 65 million years old and 120 to 150 million years old. It's also how we know of organisms that were around 350 million years ago, or even more than 500 million years ago, because of this carbon dating technique of knowing the half-life of C14. We've been using them in medical research as well. You can actually inject C14 into cancer cells, and you can watch to see if that cancer spreads. Now, this is the same technique that is used in the leaf tracer, and this is known as positron emission tomography, and it's the same kind of process, and so it's kind of like space-age technology for observing cancer tissues using C14 technology. Alright, so that's isotopes. Let's go ahead now and move on to how the periodic table is constructed. Okay, now keep in mind, here is a reduced version of the periodic table. We've actually eliminated a lot of elements to make it so it's not quite so complicated. You will notice here on the periodic table that I have 8 columns starting from the left. So there'd be 1, 2, 3, 4, 5, 6, 7, 8 columns. I also have provided you with 4 rows. There's actually more than that, but we're going to leave it at just 4 rows for right now. And remember that the top number there is your atomic number. This is your atomic weight. This is the atomic number is the number of protons. The atomic weight is the number of protons plus the number of neutrons. So let's come down to nitrogen. Where's nitrogen? Blah, blah, blah. Ah, right there. There's nitrogen. So the question is, how many protons are in nitrogen? You should have answered. I'll give you guys a second. Blah, 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 blah. Right there, number 7. Yes, remember 7 tells you the number of protons that are in there. All right, congratulations. And now how many neutrons are there? How do we figure that out? Well, we know the number of protons, that's 7. And we know that this number down here is the number of protons plus the number of neutrons. So if we just take 14 and subtract 7 from it, we end up with 7. That's right. So the number of neutrons in the case of nitrogen, the number of neutrons is the same as the number of protons. Okay, how about this one? Al. Al stands for aluminum. You come all the way down here. Here's aluminum. How many protons are in aluminum? And the answer is 13. All right, so 13 protons in aluminum. But how many neutrons are there? Now, this is a little bit trickier. Remember, there are isotopes involved here, which is what makes those numbers not quite whole. For our purposes in this class, go ahead and round the number to the nearest whole number, and that's the number you'll use. In this case, we're going to round this, 26.98. We're going to round it to 27. 27. If we round it to 27, and that 27 represents the number of protons and neutrons, then just subtracting 13 means that we have how many neutrons? 14. 14, because 13 plus 14 would be that 27. Okay, so this is an example of a potential test question, actually. I could ask you, for example, chloride. Chloride, that would be this one right here. How many protons? How many neutrons? How about for lithium? How many protons? How many neutrons? Etc. for all of these. Now, what about those electrons? We keep talking about atomic weight. We talk about protons and neutrons, but we've kind of neglected those electrons that are spinning around in their orbital shells around the nucleus. Well, they are negatively charged, and they do cancel out the protons. And so they form more of a cloud, as we mentioned before, around the nucleus. It would be unfair to really think of them as like moons orbiting around the Earth. It's not really like that. They're really just like a big cloud. Now, how many electrons does a normal, and I have that kind of in quotes here, does a normal atom have under normal conditions? Well, they tend to be equal. The number of electrons tends to be equal to the number of protons. However, that can change. We're going to talk about how it changes a little later. Electrons actually can be gained or they can be lost. But when they're under normal conditions, under resting conditions, they tend to equal the number of protons. You have an element that has 12 protons. Well, when it's under normal conditions, resting conditions, it would also have 12 electrons. Okay? However, as I mentioned, this can change, and it does change. So let's give you an example of how electrons are constructed in an atom. Electrons have different energy levels, and these different energy levels, we refer to them as electron shells. Another term that I'm going to use from time to time is valences. Valences with the letter V. V for victory. So energy levels, electron shells, and valences are all kind of going to be used interchangeably. They all mean the same thing. And that means that the electrons actually exist in different energetic states. And you can think of it kind of like distance from the nucleus. That's a very oversimplified way to think of it, but that's perfectly fine for this class here. And you can think of it like electrons that are further away, that are in an orbit that is further away than others, are at a higher energy level. Okay, so that's kind of what how that goes. And I'm going to give you some examples and the proper terminology for how to use this in terms of the Bohr model. So electrons are all residing in a shell. That is, they only exist in a particular orbit. You will never find electrons in between the shells. They only exist in either this first orbit or this second orbit, never anywhere in between. This inner shell right here, the inner orbit or the inner valence, can only accommodate 2 electrons. 2 electrons. So in the case of helium, this is the orbit that is full in a normal helium. However, the outer shell, that second shell there, can actually hold up to 8. We know this as the octet rule, because every orbit beyond that, so orbit number 3, orbit number 4, orbit number 5, if you ever get to that level, they all hold up to 8. So the only one that is different, the only one that doesn't follow the octet rule, is that inside orbit. That inside orbit, again, only holds 2. So the octet rule, we're going to try and remember that. These are some examples of atomic structures. We've already talked about hydrogen. Remember, hydrogen has just 1 proton in the middle, and it has 1 electron circling around. 1 negative and 1 positive means that when it's in a resting normal state, it is a neutral element, 1 proton, 1 neutron. Carbon, here, carbon actually has 6 electrons circling around it. It has the 2 that are on the inside orbit. Can't fit a third one there, right? Only fits 2. So the other 4 fit on the outside in that second one. Nitrogen, same thing, fills that inner shell with the 2, but 5 on the outside. But now I want to jump over to phosphorus. Oxygen we'll come back to later. In the case of phosphorus, it's got 2 on that inner shell. It's filled that second orbit with all 8, and then it has an additional 5 more here in the outer shell. So how many in total is that? Well, you count 2 plus 8 plus 5. Phosphorus has 15 electrons circling around its orbit, so circling around its nucleus. And then sulfur has even more than that. So this is how electrons are drawn in a typical Bohr model. Now, is there a way to predict how chemicals react? The answer is absolutely yes. You simply need to know how many electrons the atom has in its outermost shell. So, if it's filled a shell, and then it actually has to move out to another shell to add more electrons to that, that's what we're concerned with, is how many electrons are in the outermost shell. Okay? So that is really what chemistry is all about, is predicting reactions in atoms. And so what we're going to be doing from now on is counting electrons to determine its reactivity. And at this point, if you need to take a break and review the material up to now, this would be a good stopping point, and you can come back to slide number 28. For those of you that want to go on, let's continue. How many electrons are in the outer shell of this particular element? Well, you have to determine the number of electrons and fill in the shells. So, for example, here we have our 2 electrons on the innermost shell. We have our 8 electrons in the second shell, and this particular element, this particular element has 8 more electrons in the third shell. So from this information, I can actually predict which element this is on the periodic table. And so this is going to be really helpful. So on the periodic table, not only can I ask you how many neutrons and protons there are, but I can also ask you how many electrons are in a particular element. So I want you to pay attention to a couple of things now. I mentioned the columns and I mentioned the rows, but it turns out that these actually have relevance. They are very important for predicting the number of electrons that are in an atom. So the columns actually refer to the number of electrons that are in the outermost shell of an atom. Now, I'm going to show you this in just a second here. The rows refer to the number of shells that are occupied by electrons. So in the case of carbon, if you have to back up, you can take a look at the carbon Bohr model, although we're going to cover this a little bit here in just a second. The carbon Bohr model has an atomic number of 6 protons. Well, if it has 6 protons and it's stable, how many electrons does it have? For those of you that have been paying attention, the number of electrons is the same as the number of protons. So if you have 6 protons, then carbon should have 6 electrons. Okay? And how many neutrons does it have? Well, it's 12 minus 6 because we're rounding this to 12. So this element, and this is something I could certainly ask you on an exam, the element carbon, how many protons does it have? 6. How many neutrons does it have? 6. How many electrons does it have? 6. Okay, that would be the answer there. Let's go ahead and take a look at some examples here. I want you to name the element. Let's go ahead and start on the left. Well, here we have an element with only one electron in one shell. Well, remember, the rows tell us how many shells or how many orbits there are in this atom. We've said that there's only one here, so it has to be on this row here. Okay? And there's only one, which means that it can only be in this column. Well, if it's in this row and this column, then this must be helium. I'm sorry, this must be hydrogen. Hydrogen right there. Let's go to the other side. What about this one over here? This one also only has one orbit, which means it has to be in row number 1. But it has two electrons in its outer shell. If it has 2 electrons in its outer shell, then essentially it has a full shell, and therefore it is helium. How about that? Can you do that on an exam? Let me give you another one. How about this one? This one's a little bit more complicated. All right, so let's narrow it down. How many orbits does it have? It has 1, 2. It's got 2 orbits, so it's got to be in row number 2 somewhere. Okay, row number 2. So now let's count the number of electrons it has in its outermost shell. Just in the outermost shell, because that's where it's most reactive. That's where it's going to react with other atoms. It's got 1, 2, 3, 4, 5, 6, 7. So let's go over here to column 7. Column 7 in row number 2, it has to be fluorine. That's fluorine right there. Now let's do another one. How about that one? Again, we are in row 2 because it has 2 orbits. 1, 2. And it's filled its inner orbit, but it's got three electrons in its outer orbit. 1, 2, 3. Which means that we have to be in 1, 2, 3. Column 3 in row 2. That's boron right there. Boron. Now, let's do a little trick here. Boron, what is the atomic number? 5. Because it has what? 5 protons. How many neutrons does it have? Well, we're going to round that to 11, and we know that 11 minus 5 is 6, so it has 6 neutrons. But how many electrons should it have? Well, if it's neutral, then it should also have 5 electrons, right, to equal the number of protons. Look at this. 1, 2, 3, 4, 5. So everything agrees. Everything agrees. Excellent. Let's do another one. How about this? This one also. Only 2 orbits, so we must be in row number 2 here. This one has 1, 2, 3, 4, 5, 6. 6 electrons. So 6 electrons means column 6. That would be oxygen. Oxygen is the one with 6 electrons and happens to be in row number 2. And then you can go through the exercise of counting the protons, counting the neutrons, using the atomic mass, and then also trying to predict how many electrons it has, and then come back to here and go, oh yeah, that's correct. It has the proper number of electrons, 2, 4, 5, 6, 7, 8, to equal the number of protons. All right, let's move on. Let's do one more. A little bit more complicated. This one has 3 orbits. 1, 2, 3. So we must be in row 3. Row 3. It's filled its inner shell with the 2. It's filled its second shell with the 8. But the outer shell here has 2, 3, 4, 5. Column 5, row 3. That's phosphate. How about that? Now, can you do that on an exam? Can you tell me how many protons there are in phosphate? You should say 15. Can you tell me how many neutrons? You should know that that rounds to 31. 31 minus 15 is 16. There are 16 neutrons. And how many electrons should it have? Well, it should have 15. Are there 15 here? I'll let you count it. Let's move on. So if I was to take the periodic table and just show you the Bohr models for all of those with the electrons spinning around them, this is kind of what it would look like, something like this. And you'll notice that as you move from the left to the right, you go from having only one electron in the outer shell. This one only has 1, that one only has 1, that has only 1. all the way over to column 8. In column 8, all the outermost electron shell has been filled. So in this case, the outer electron shell is filled, the outer shell here is filled, and this one, because it's only that inner orbit and it only takes 2, that one's filled as well. So let's actually talk a little bit more about stability and when atoms are more stable. Turns out atoms like to be stable. And how do you be stable? Atoms like to have their outermost shell full. They like to have it full. And remember, that inner shell only takes 2. All subsequent shells out here can have up to 8. Atoms tend to move towards stability. And they do this by gaining or releasing electrons to fill or empty their outer shells. So take a look at this particular atom here. In the outermost shell, it has 2. But what would make it happy? What would make this atom happy is to have a full outermost shell. So let me ask you, what's going to be easier? Is it going to be easier to lose 2 or gain 6? Well, to answer that, we need to take a little bit of a detour here. A little bit of a detour. I'll just give you a hint. Losing 2 is probably a little bit easier than gaining 6 more to make a total of 8. So filling vacancies is really what this is all about. If there's only one electron in the outer shell, it is more like, let me ask you, is it more likely to gain 7 or lose 1 to get stable? Well, you should really think of it as kind of the analogy of which would take more effort, adding or subtracting to it. And hopefully you will see that it's probably easier to lose 1. I hope that didn't scare you guys. It's probably easier to lose 1 than it is to gain 7. Okay? So this atom here has now lost an electron so that it can feel a little bit more stable. But in the process, something magical has happened. It's actually taken on a charge. So let's go ahead and take a look at this case right here. If you have 6 electrons in the outer shell, are you more likely to gain 2 or lose 6? What do you think? Well, hopefully you've said 1, 2, gain 2. Yay! You got it right if you said gain 2. If you didn't say gain 2, rewind about 15 seconds and then you can feel like a pro because you can say gain 2 again. Okay, so is the outer shell half empty or half full? Well, it turns out that all of those elements that are on the left side of the periodic table, all the elements over here, these are the ones that have either 1, 2, or 3 electrons in their outermost shell. And you might say, well then the elements in these 3 columns are more likely to give up their electrons to reach stability. Okay, we refer to those as metals. The elements that are over here tend to be metals. On the other side, let's say 5, 6, and 7. 5, 6, and 7 over here, and in this note here I've included 4, but 4 is a special case. Let's just think 5, 6, and 7 for now. These are the elements that have their shells almost full, and so they are more likely to gain than to lose electrons. The elements that are on this side of the periodic table, we call those nonmetals. Okay, we call those nonmetals. Now the special cases here, we're going to deal with column number 4 in just a couple of slides because carbon and the elements that are below are actually kind of special because they're right in the middle. They are not always going to give up their electrons, and they're not always going to be gaining electrons. They are actually going to be sharing them more often. But we're going to discuss column 4 a little later. Let's come over here to column 8. Column 8 is very unreactive because it's already got its outer shell full. It's not going to gain and it's not going to lose because it's already there. So these things, helium, neon, argon, and krypton, are the noble gases. These are the gases that are very unreactive, and it's because their outer valence shells are already full. So What happens to these elements when they either lose their electrons or gain electrons to get a little bit more stable? Well, we call those ions. Ions are elements. They are elements that have gained or lost electrons. Normally, under normal conditions, atoms have an equal number of electrons compared to their protons, so they have no net charge. But if you lose electrons to get stable, it means that you're going to have more protons than you have electrons, and you're going to be positively charged. Hence, metals tend to be positively charged. On the other hand, if you tend to gain electrons, that is, you're grabbing more electrons than you have protons, then you're going to have a disproportionate negative charge. These are the nonmetals. Nonmetals tend to be negatively charged. And it is these negative and positive charges of these ions that actually form one kind of chemical bond. And all molecules, all compounds are bonded together, and the negative and positive aspect, the negative and positive ionic charges, is one way that you can bond atoms. So what is a bond? I have here a bond is defined as a union between electronic structures of atoms. And when atoms bond together, they form molecules. So let's talk a little bit about these bonds now. There's actually 4 different kinds of bonds, and we're only going to focus on a few. We're not going to focus on all of them. We have strong chemical bonds, like these ones right here. Strong chemical bonds are really hard to break. Covalent bonds, that's what are our strongest chemical bonds, covalent bonds. The other 3 different types are known as weak bonds. We're going to talk about 2 of them here and not so much about this 4th one, although I'll give you a picture of what that looks like. Ionic bonds and hydrogen bonds are very important in biological systems, as are covalent bonds. And so let's go ahead and talk a little bit about covalent bonds first, then we'll jump down here to the weaker bonds. Covalent bonding is when atoms actually share electrons to fill their outermost shell. Take a look at this hydrogen. You remember hydrogen only had 1 electron spinning around it? Well, when a hydrogen and a hydrogen get together, their one little electron can actually fill both orbits. And when that happens, each of these hydrogens, quote-unquote, sees 2 electrons. Well, this hydrogen doesn't care that it only started out with 1. All it cares is that when it combines with this hydrogen, it now sees 2, and it feels stable. So hydrogen gas, which is H2, this is hydrogen gas, is stable because as far as each of these hydrogen nuclei are concerned, each of them sees 2 electrons and therefore behaves as if their outer shells are full. In the case of oxygen, oxygen gas, O2, is 2 oxygen elemental atoms that are set side by side, and they actually share not just 1 electron, but they actually share 2 pairs of electrons instead of just 1 pair. So remember, oxygen, if you go back to your periodic table, has 6 electrons in its outermost shell. And with 6, that means that each one needs 2. Well, if they share 2 pairs, then as far as this is concerned right here in the nucleus, it sees 1, 2, 3, 4, 5, 6, 7, 8. It sees 8 and it feels stable. So for that reason, oxygen gas is very stable. So covalent bonds are exactly what makes water stable too. Classic case of water. Here you have hydrogen. Remember, hydrogen has just 1 electron circling around the nucleus. And oxygen has 8, but 2 are in the innermost shell, and 6 are in the outermost shell. Oxygen really would like to have 2 more electrons in its outermost shell. Well, what great way to do it than to combine your efforts with 2 hydrogen atoms. Here are 2 hydrogens here, and we can count up the number of electrons, and it's 1, 2, 3, 4, 5, 6, 7, 8. Again, as far as this oxygen nucleus is concerned, it is seeing 8 electrons, and it feels stable. As far as these hydrogens are concerned, they too are seeing 2 electrons and therefore feel stable. And for this reason, water is extremely stable. So covalent bond, this is why covalent bonds are extremely strong. So let's go on to that second kind of bond, ionic bonds. And ionic bonds are really all about battery charges. You can think of them as acting just like battery charges. When one atom loses an electron, it becomes positively charged, and when another atom gains an electron, it becomes negatively charged. And so a negative and a positive atom or ion tend to attract each other. And so the classic case of this is the formation of table salt, sodium chloride. Remember, if you look back at your periodic table, sodium has only a single electron in that outer shell, whereas chlorine has 7. Well, this chlorine really would like to have another electron, and this sodium really would like to give up its extra electron. So when the two of these get side by side, they actually swap, producing sodium with a positive charge because it's missing an electron, and chlorine, or chloride, which has a negative charge because it's gained an electron. And so this has an interesting outcome to it, because when you put these positive and negatively charged ions next to each other, they end up forming a lattice, like a battery. Each one is attracted to the other. And that's kind of nice. So a typical ionic compound is held together by ionic bonds. These are not strong bonds. If you were to take salt crystals and throw them into water, what would happen? It immediately breaks apart. So water is very easily able to dissolve table salt. Table salt is not a very stable compound, and it's because it's held together by ionic bonds, not covalent bonds. Now, the third kind of bond, hydrogen bonds, are an interesting kind of phenomenon because they are formed when hydrogen atoms are covalently bonded to another atom. When hydrogen atoms covalently bonded to another atom is also attracted to another atom next to it. So for example, you see this hydrogen right over here? This hydrogen ends up becoming attracted to other elements, to the elements of other compounds simply by its magnetic attraction, by its battery-like attraction. Remember, hydrogens are basically positive for the most part, and so they tend to be attracted to things that have a slight negative charge to it. Water is a classic example of this. And so in living cells, what we call the electronegative partner is usually something with a slightly negative charge, like oxygen, or in this case, nitrogen. Since nitrogen is slightly negative and hydrogen is slightly positive, they have this tendency to connect with each other. And that's called a hydrogen bond. We're going to talk a lot more about hydrogen bonds later because the way that DNA is constructed actually has to do with this. Now, I mentioned that I'm not going to dwell on that fourth force, van der Waals forces, but it has to do with the asymmetry of some elements, of some compounds. Some compounds tend to have a slightly negative side and a slightly positive side, and they create weak attractions between molecules. And the classic case of this are gecko toes. The reason that geckos are able to walk on glass and stick to it is because of the van der Waals forces on their fingertips. So again, we're not going to go into any great detail on this, but we will focus on the other three. So let me ask you this. We now know about metals, we now know about nonmetals, about the sharing of electrons, about covalent bonding, about ionic bonding, and hydrogen bonding. Well, how about this particular element right here? How is it going to behave? Is it going to gain or is it going to lose? Well, as you might have suspected, this is actually an unusual case. This is carbon. Carbon has four electrons in its outermost shell. And rather than giving them up or gaining, carbon tends to share. So it's much easier to share. And this is what makes carbon a unique element. And so therefore, carbon never behaves, or I should say almost never behaves ionically, and instead it tends to behave covalently, which means that carbon bonds are among the strongest in the natural world. So let's talk a little bit about carbon because we're going to focus on it, and it's a very, very important compound or constituent of organic compounds. So what is its atomic number? Okay, well, from the information up at the top there, you should say 6. 6 is its atomic number, and then you would have gotten it right. What are the number of protons? Well, that would be 6 too. What are the number of electrons? 6. Right there, see? That's how you would arrange them. See, if you were to draw that on an exam, you would put 2 in the innermost shell, and then you'd put the remaining 4 in the outermost shell. How many are in that outermost shell? Well, obviously the answer is 4, but if I didn't give you this Bohr diagram and all you had was the periodic table, this box right here, you should still have been able to tell me that there were 4 electrons in the outermost shell. Okay? What about the behavior? Well, you should also be able to tell me that since it has 4 electrons in its outermost shell, it is actually going to share those electrons. It's more likely to be covalently bonded to anything else. So it shares 4 electrons. Now, this is a nice drawing, but unfortunately it gives the false impression that the orientation of these electrons here is at 90 degrees to each other. And that's actually not true. You see, we're dealing with carbon here, and carbon is a 3-dimensional element, right? In space, these things are 3-dimensional. They're not flat on a piece of paper. So it might be nice to draw this line or stick diagram. A lot of people do, connecting up their hydrogens like this, but we need to remember that this is actually not flat. It's a 3-dimensional object, and in fact, it's in a shape known as a tetrahedron. This is it right here. This is actually what a carbon compound, in this case a carbon compound with 4 hydrogens on it, would look. It would look like this, a tetrahedron. If you were to actually measure the angle here between each hydrogen, each one of these bonds, it would be 109 degrees. 109 degrees. That's actually kind of interesting. So this is known as a ball and stick diagram. Okay, and carbon is really great for building molecules because of that tetrahedron design. You can actually connect these things up and make really cool 3-dimensional structures. This neat thing down here on the left is called a polyhedron. Also looks like something called a buckyball. You can look that up. I'm not going to ask you to memorize it, but buckyballs are actually kind of cool. 3-dimensional balls in space made up just of carbon atoms. And organic, this is where we get the term organic. Organic compounds are ones that are heavily made up of carbon. So things are organic if they have lots of carbon in it. Some typical organic molecules look like this. We're going to go into greater depth on what these things are. Glucose on the left, phospholipids on the right. I know they sound like big words, and those things look really impressive and scary. But you know what? When you just look at them, it's just a string of carbons with a whole bunch of hydrogens and oxygens kind of connecting up to them. That's all it is. This one's fancy because it has a phosphate in there, a phosphorus. But you shouldn't be scared by any of these things. We're going to break these things down a little bit later. But we want to now kind of talk about the reactivity of some of these elements. What makes them reactive? So let's go ahead and play with this particular element, nitrogen. How many bonds will nitrogen form? Okay, can you actually draw this out on a piece of paper? In fact, you should probably do that. Take out a piece of paper and try and draw this. Nitrogen. What's its atomic number? 7. What's its atomic mass? 14. What does that mean about its protons and its neutrons? It has 7 protons, so says this number up here. It has 7 protons here, 7 neutrons, because we can take 14, subtract 7 from it, and that gives us our neutrons. How many electrons does it have? Well, if it's stable, it should have 7. Okay? Well, if you're going to arrange those 7 electrons, how do you apply them? Well, don't forget, you're going to, so these are all of the things that you have just told me, right? you fill its inner shell with the 2, and then you take the remaining 5 and you put them on the outer shell. So when we ask how many are in its highest energy shell, you should tell me 5. There are 5 in its outermost shell. And there are many different ways to draw it. This is one way. And why do we draw it this way with 3 lines? Because this pair of electrons is unreactive up here. It's not going to combine with anything. It has 1, 2, 3 areas that it can react. Okay? It can form up to 3 bonds. So this is actually kind of important because it tells you the reactivity of each different element on the periodic table. Now, let's talk chemistry. We use symbols to write out formulas to refer to chemical compounds. And so, as an example, this is glucose right here. Glucose is a sugar. It is, we give it the designation C16H12O6. That sounds kind of fancy, but really all it means is that the molecule, the sugar molecule, has 6 carbons, 12 hydrogens, and 6 oxygens in the compound, right there. That's all that really means. So it shouldn't be too daunting to you. If I was to show you this on an exam and ask you to tell me this kind of information here, that should be rather easy. So chemical reactions occur by just recombining the elements, or recombining the elements that are in the compounds to form other compounds. And the classic example here is this reaction. This is photosynthesis. And where we take the reactants, these are the reactants over here, we take some carbon dioxide out of the air, take a little bit of water out of the soil, we add some energy magic here. Of course, it's not energy magic. We add the sunlight to it, and voila, presto, out the other side we end up with glucose, which is a sugar, and oxygen. This process we're going to discuss in greater detail, but here's what I want you to pay attention to. You can actually count up the number of carbons, the number of oxygens, and the number of hydrogens on this side of the equation, and they should equal the number of carbons, hydrogens, and oxygens on this side of the equation. For example, this number out here tells you how many of these compounds you need. Of this carbon dioxide, you need 6 of them. So if you have 6 carbon dioxides, then you also have 6 carbons. Over here in glucose, look at that. Here's your 6 carbons. So the 6 carbons from here were recombined in the process to be incorporated into the glucose. Okay.